Right. So let me do a quick recap of yesterday, at least to remind you of what were the key messages. So roughly I started my talk by arguing that now we have many experimental platforms where we can essentially explore the entire phase space of configurations. And from the point of view of complex matter theories, what that brings the question is, okay, what are the relevant degrees of freedom that dominate dynamics, given that now you can explore all possible energy and length scales? And a second order question is actually, is there anything universal about these, let's say, regimes, about these far from equilibrium or far from ground state behaviors where you no longer have this dilute number of quasi-particles. And basically, the main point or the main take-home message of yesterday's lecture was that even when you consider a simple model, and I essentially focused the entire lecture on a well-studied model in the literature, which is a weakly interacting Bose gas. Essentially what we found is that there's no such thing as one pathway to relaxation. There are potentially multiple pathways of relaxation depending on what are the relevant degrees of freedom. But also each, let's say, each regime is characterized by different scaling exponents. Or different universal properties which are manifested in correlation functions. And I argued that at least from my point of view, always a good starting point to discuss these far from equilibrium regimes is asking the question of how symmetries, how constraints, how dimensionality can hinder or can arrest relaxation in some non-trivial way. So far, so good. I don't know, is there any question about yesterday's lecture? No, okay. So let me start today. Again, the Boson model is a very well-studied model. I wanted to motivate this lecture by arguing that also in the last few years, there has been also remarkable progress in studying spin systems. Particularly these images date back from the time when I was a postdoc at Harvard, where there were a lot of, even within a single university or also within MIT, there were a lot of experiments going on where now it's not bosons which are let's say, driven out of equilibrium, but it's more spin systems. For example, in this first case, a typical example that you can do nowadays in experiments is, for example, grab ferromagnetic insulators and drive them, pump them very hard at the ferromagnetic resonance and create a far from equilibrium distribution of quasi-particles. I also mentioned yesterday MP centers, which are random ensembles of spins where you could potentially initialize a system in essentially in an infinite temperature state. Also in cold atomic gases, where now atoms are no longer allowed to move in the lattice, but they are fixed, and you can play with the internal degree of freedom of the spin and essentially achieve a spin insulator and realize interesting experiments in far from equilibrium regimes. So more or less to set the stage, how many of you have worked with spin systems or? Oh, okay, good. Actually, a big. So yes, yesterday Jamir was mentioning that there was supposed to be another speaker who would actually introduce all the necessary material, but I will try to make my talk self-consistent and go through all the details for those of you who are not familiar with spin Hamiltonians. At least from the questions I've been hearing in the other talks, it seems that many of you are let's say, very well versed on field theory techniques, which are usually tailored for bosons and fermions. But spins also have a little bit additional challenges that one need to take into account to describe dynamics. So I will start with the simplest model that we can think of. So essentially, I will be discussing almost entirely the Heisenberg model, which is, I would argue, one of the simplest models of quantum magnetism. And basically, what I will be assuming is that I'm working on a d-dimensional. Again, I don't want to specify dimensions. Let's assume this is a d-dimensional lattice, square lattice of spins, where on each side I have a spin s degree of freedom. We can set s to 1/2, so we can have the local Hilbert space has 2 states. But in reality, one can also think large s some classical limit, and that's perfectly fine. It's not really going to change much of what I have to say when it comes to far from equilibrium regimes. So maybe we can do some analogies. If you want, we can. There are analogies between spin models and bosonic models. Maybe we can analyze the 2 terms separately. So one can ask, what is this term doing? By the way, here I'm talking about the nearest neighbor interactions. Actually, something I didn't mention yesterday, but also is important. Another important constraint that you have in systems, in addition to symmetries and dimensionality, is spatial locality. That's something I forgot to mention. You could also think about systems where you have all-to-all interactions, but in everything I will be discussing, there's always, I will implicitly assume spatial locality. And for those not familiar with spin models, essentially you can ask what are these 2, the first 2 terms, the XX and YY term, what are they doing on spins? This would be essentially a spin flip operator. So for example, if I if I take 2 spins which are neighboring and the 2 spins are up, this will do nothing to the state. Essentially, you can do the calculations yourself. So if you do SX, SX on a spin up and spin out, basically you are flipping the 2 spins. So this you will get a down, down. And then when you do SY, SY, you are also flipping the 2 spins, but you are acquiring a minus I squared. So essentially this vanishes. Alternatively, if you apply the this spin flip operator on a state where, for example, I have a spin up and spin down, what you can convince yourself is that this will essentially exchange the spin up and spin down. And of course, the same happens if I do up, down, up, or if I do down, down, you will also get 0. So in a very loose sense, imagine that I start from an initial condition where all the spins are up. Let me use some color. So in simple terms, if I start from a configuration where all spins are up, and let's assume that I randomly flip a couple of spins here and there with a small density. What this Hamiltonian would do in the absence of the ZC term is these spins would be essentially hopping throughout the lattice. And you can essentially do an analogy with essentially a bosonic model where you have hardcore collisions. You don't allow 2 spins to be on the same side. So in that sense, this model looks very similar to a bosonic model, we can ask what is this term doing, the Sijzz. So as you can imagine, this would essentially create an interaction term if there are two spins which are very close to each other. So if the two spins are very far from each other, this essentially is slightly changing the energy of a local spin flip. Again, let's think about this scenario where most spins are up except a few of them. So for example, if I have just one spin moving through the lattice, this would acquire an extra energy due to having two. So here I will acquire 2 times delta. Whereas if I have two spins which are nearby each other, for example, up, down, down, up, there would be a reduced energy because now I will have 2 delta rather than having 4 delta if you would have 2 independent spins which are far from each other. So there would be effectively a sort of attractive interaction which would be minus 2 delta. So far, so good? Okay, so essentially this is the model. So again, just to recap, you can think about it as spin flip moving around the lattice. You don't allow two spins to be on the same side. And also this delta is giving rise to some sort of effective interactions if two spins get close together. There are some differences with the bosonic model. In particular, here we have the local Hilbert space is 2, or in the case of spin 100, it will be 2. And if you plot the spectrum, basically what this means is that the spectrum is bounded for the Heisenberg model. If I plot all the density of, so this is essentially density of states. If I draw a histogram of all possible energy levels, you will see that this is no longer unbounded. So in the case of a Bose gas, I can always put enough kinetic energy to a boson, and that's it. You can always go to infinite energy. Here, the infinite energy case would be essentially a paramagnetic phase, where if you start from a system which has a very large energy, spins would be locally fluctuating randomly or separate, like independently of each other. If you go to very low energies, because I added a minus sign, so here I added a minus sign. Essentially, the ground state is the ferromagnetic ground state. Essentially, all spins will want to be aligned with each other. So in this case, you reduce energy if spin configurations are pointing in the same direction. This ground state in particular is classical. It's just the product state of all spin pointing up. If I look at the other end of the spectrum, this would be equivalent as just flipping the sign of the Hamiltonian. So in this case, you would want the spins to anti-align with each other. Up here, you would have the antiferromagnetic ground state. Where unlike the ferromagnetic state, the antiferromagnetic ground state is quantum, it's not classical. One way to see this is that if I propose a classical solution of a staggered magnetization where, for example, each spin, here I'm thinking of a one-dimensional lattice, but forget it, that dimensionality doesn't matter. If I plug in a configuration where I have spin up, spin down, spin up, spin down, which is a classical configuration, and you apply the Hamiltonian, you will see that this term, the hopping term, will flip the spins, and this will not be an eigenstate of the Hamiltonian. So if you want to do if you want to find the actual ground state of the antiferromagnet, you have to work a little bit harder. it would be a fluctuating state, so there would be quantum fluctuations even at 0 temperatures. So far, so good. So that more or less to give you a broad a physical intuition of the model. Now I want to say something more specific. The interesting regime that I will be considering is the isotropic case, so when there's a global SU2 symmetry. So in particular, in what follows, what I will do is I will set delta to 1. Essentially now, now it's slightly different to the bosonic model because there's an additional symmetry. It's essentially now you have a global SU2 symmetry in the model, which essentially means that now I have 3 charges. So my Hamiltonian commutes with X, Y, and Z. This is the total magnetization. And also there's an interesting point that will come out later on, is that usually when you have an anisotropic Heisenberg model, for example, an XXC model, you have a specific reference frame, which is the z-axis, where you can do your, where you can analyze, which you would normally use as a basis to describe your state. Once you have SU2 symmetry, in reality, there's an ambiguity of which is your right reference state. And that's particularly important when you initialize your system, let's say let's say you start from an excited state that has 0 net magnetization. So then there's no right reference frames. There's kind of like a gauge degree of freedom of what is your right orientation. And I will argue that that will lead to interesting dynamics as the system approaches equilibration. Okay, so now we can repeat. Okay, is there any question about the model? No. So now essentially what we can do is repeat exactly the same type of arguments that we applied yesterday, asking the generic question of, let's assume that I start from some product state of spins where it's an excited state, and I ask the question, is there anything generic or anything universal about thermalization? And what we can do is exactly the same exercise, asking the question, okay, what are the potential constraints or the potential degrees of freedom that can dominate in this prethermal regime? For that, we can use some intuition. It's exactly what we did yesterday. We can use some intuition from thermal physics of matter. So let's assume that E is the energy of my initial state. Let's assume that I'm in high dimensions. So let's assume I'm in 3 or higher dimensions in the Heisenberg model. So I know that in higher dimensions, if energy is small, that there can be essentially symmetry breaking. So the system can organize, there could be long-range order into a ferromagnetic phase. It could also be an antiferromagnetic phase if I flip down the spin, doesn't matter. And if I initialize my initial state above this critical energy, I would know that I will end up in some paramagnetic phase. So this is essentially, this is kind of the phase diagram of the Heisenberg model in 3 dimensions. So there's a critical energy or a critical temperature below which there's a tendency towards ordering, and there is a tendency, towards disorder. So the paramagnetic phase, essentially what it means is that all spins are fluctuating independently from each other. They behave as independent, thermally fluctuating. So there's nothing particularly interesting in this regime. Unlike the Bose gas, where if I push the system to very large energies, I could still have weakly interacting particles. I can still have weakly interacting particles, and there's still an interesting regime. So in this case, because the phase space is compact or is constrained, this regime would not be of interest to me. Yeah.
Yeah, so just a quick question to understand the setup. So, and here, like you imagine that we initialized the model, like in some initial state, like some generic initial state
Yeah.
with energy,
Yeah.
which which is below this like E star, like the expectation value of the energy in that state is below, say, this E star, and then like you claim that like if we are in this dimensions, like, I don't know, probably like above 2 or something, like we'll generically just like, you know, like sort of flow to this ferromagnetic sort of like state
Yeah.
in the end, or
Right. In the right. So in the what I will try to do is kind of the argument like yesterday. So at long times, all spins will tend to order, and in particular, let's think about it. There will be a tendency towards ordering at long times. In particular, if you are thinking what happens at long times, also because you have SU2 symmetry and 3 dimensions, you can also form skyrmion, you can also form topological defects. So there could be much more physics going on. Uh, um, but the general rule, as a rule of thumb, is if energy density is not large enough, there would be a tendency for spins to locally organize, even if globally they are not. Because you may start from it could be like what I discussed yesterday, of course, in dynamics, where maybe some spins will tend to align in one direction, other spins will tend to align in opposite directions. You can form either domain walls. In this case, what you will form is skyrmions. You could potentially form localized defects. I will do some sort of mean field arguments later on to argue that here you would tend to, like the order parameter will be stiffer, will be stiff. So essentially you can think of this as a globally ordered state, even if there are regions where in reality there's ordering in different directions. I don't know if that answers your question.
yeah, I think so. So below this E star, I'll have like some spontaneous symmetry breaking
Yeah.
state. Okay, and it might have a different nature, as you mentioned, like skyrmions or something like that. But like,
It could, right. So, okay, something I also remind you from yesterday, I will always be talking about isolated systems. So I'm not controlling, so the energy only appears through the initial state. So that's correct. So there could be 2 things that could happen. First of all, spins would tend to align in long-range order, but you could also form skyrmions, which would be localized defects, so essentially point-like defects, which you can think of gas of classical particles.
and there would be no phase transition between those 2 things.
Define phase transition.
Oh yeah, so I just mean like, so like, could I say adiabatically connect, like, say, this like skyrmion ground state and like this conventional ferromagnetic state, or
No, I would say it's more like what we discussed yesterday, where if you start forming topological defects, you will have a new length scale in your problem.
oh, I see.
So when you start looking at correlation functions, you will ask the question, okay, which length scale am I zooming into? And then what is the mechanisms that it's governing dynamics at that length scale?
Cool, yeah, perfect, thanks.
So, right, so remember, it's always 2 things. It's also energy, but also there's also a length scale issue where different things could happen at different scales. So if you are in 2 dimensions, you have, so this is a continuous symmetry. You have Mermin-Wagner, which prevents forming long-range order, but you can still form long-range order at temperature 0. So in this case, there's not really a critical energy, but you can ask the question, and I will ask this question later on, that maybe if you initialize your system at low enough energy, you will feel these ferromagnetic fluctuations governing dynamics, at least at some energy scale. And the one-dimensional case is, okay. The one-dimensional case at least for the purposes of my talk, would be kind of boring, generally, because you always have a paramagnetic phase. So it could be interesting to study from hydrodynamics, or in the case of spin 1/2, you have the issue that you have integrability. So if you have Heisenberg model in 1 dimensions, and you have spin 1/2, then you have to deal with integrability, which I'm not going to be talking about in these lectures. So I will leave this case aside. I will mostly be focusing on the D equals 2, which seems to be, I will argue that probably is the most interesting case. Okay, so far so good. Yeah.
So there is no chance to have antiferromagnetic order.
Well, no, no. Well, you can. So you can think. You see, you starting from the ferromagnetic case.
Mm-hmm.
Right. So you can start from an initial condition where you order the spins antiferromagnetically. So then you would be up here in the spectrum. So in the inverse temperature regime, where you have lower density of states at higher energies, and you would be probing the antiferromagnetic ground state.
Okay.
So,
and why is absent in the diagrams that you are now sketching, this antiferromagnetic?
Well, it would be like it's essentially the same, right? You have long-range order.
Okay.
So you would have right. So if you keep going in energy and you end up on the other side of the spectrum where there's negative temperatures, you will start probing. And I will make if we have time towards the end, I will focus because it's the simplest case. I will just focus on the ferromagnetic case. But we also have, in fact, we have results, a recent work where we actually probe this antiferromagnetic regime. So if you understand how to do the ferromagnetic case, doing this one is kind of trivial. Or not trivial, but it's different, but you still apply the same line of thought.
Thanks.
So let's start with the simplest case where, again, I will assume that to start doing some calculations, I will assume that I start from a configuration which is most spins pointing up, and experimentally I go and I flip a couple of spins. So the conditions that I will be considering is that the number of spins which are flipped over the total number of spins. This is L to the D, so L is the linear dimension of the system. This number is much smaller than 1. So this case, there are various ways in which one can analyze this case. Probably the most standard way would be to do Holstein-Primakov. Everyone is familiar with Holstein-Primakov? Yeah, okay. I will remind you for those of you who are not. But essentially, we can transform spin operators in terms of bosonic operators and write an effective bosonic theory that describes the regime in which only a dilute number of spins are flipped. So the key idea of Holstein-Primakov is doing a transformation. Let me write it up, where the SZ operator, so each spin at each site, I replace it. I use bosonic degrees of freedom. So here in each site, I replace the spin operators by bosonic degrees of freedom. So these have the canonical bosonic commutation relations. You can convince yourself that if you apply the usual spin operator commutation relations, you will find the usual results in terms of bosonic operators. There's a big price that you're paying when you do this transformation, and is that you have these square roots. So in principle, you would have to expand these to infinite orders. So if I apply this transformation on the Hamiltonian, I could, of course, start expanding to quadratic order. I can start expanding to quartic order. But in principle, because I have this square root, I should, if I want to do exact calculations, I need to go to infinite order. But usually, the approximation that one uses, and is the one I will be using, is because the number of spin flips is relatively small, you can just keep the leading order quadratic and quartic terms to write essentially an effective bosonic theory that accounts for the motion of spin flips plus the interactions. Yep. So one way to do it, I leave it to you as an exercise. You can plug in this transformation on the original Hamiltonian and find the effective Hamiltonian to quartic order. What I wanted to do is some alternative pathway to find effectively how spin flip interactions interact with each other by just finding exactly the eigenstates of the Hamiltonian, which in the Heisenberg model is relatively easy to do. Essentially, what I would be constructing is the exact eigenstates of the Hamiltonian as I start increasing the numbers of spin flipping in my lattice. So let me start with, so I already mentioned that the ferromagnetic ground state is the classical state with all spin up. So essentially what I will start doing is I will focus on a single spin flip, and I will define essentially the spin flip operator. So here I didn't define it as plus. Plus minus is where essentially what I'm doing is distributing all the spins, the spin flips over all the lattice sides. So I'm taking Fourier transform. So here V is the d-dimensional volume. And what you can show is that if you apply the SK plus operator on the ferromagnetic ground state, so essentially, effectively here you will have a one spin flip in the entire lattice. And I apply the Hamiltonian to this state. So again, this is a state that will have a superposition of spin flips in all lattice sides times the Fourier component. So essentially, I'm doing the Fourier transform of where I'm placing the spin. So there's a degree of freedom, which is k. What you can show is that if you apply commutation of this operator with the Hamiltonian, what you will find is that so essentially, here what I'm doing is moving the spin operator to the left, applying commutations with the Hamiltonian. And what you will get is this term, which is nothing else than what's called the spin wave energy, where the gamma, let me first define these gamma functions, this gamma k. This is just the sum basically, it's a phase factor where you are summing over all possible nearest neighbors multiplied by the k vector. And what you will find is that the energy of the spin wave scales as k squared. So essentially, if you grab it a traditional solid state physics, what you will find is that these are exact eigenstates of the Hamiltonian. These are spin waves. Spin wave solutions which have energy dispersion, which is k squared. And these are exact eigenstates of the Hamiltonian. Now you can ask, let's assume that now I move into one additional symmetry sector. So now I have two spin flips in my lattice, and you can do exactly the same exercise. So let's assume you create two spin wave excitations at two different wave vectors. And you ask the questions whether this is eigenstate of the Hamiltonian. again, you have to do the same exercise in which you try to move the spin operators to the left of the Hamiltonian, applying commutations. It's a little bit of a tedious exercise, but what you would naively expect, at least from what you would read in a solid state physics textbooks, is that this will have energy of 2 spin waves. So the naive expectations is that this is also an eigenstate of the Hamiltonian, but in reality that's not the case. If you do the calculation carefully, you will find that in addition there would be a term, an interaction terms between spin waves, which is the same gamma. Let me look it up. Okay, so let me make a physical sense of what I'm writing. So if you write if you are focusing only on the symmetry sector where you have only 2 spin flips, and you create this state, what you would get is a diagonal component in the Hamiltonian where you have the energy of each spin flip independently, so the spin wave eigenstate. But in addition, you will get an interaction term. So you will have a matrix elements that basically couples these K and P spin waves with all other spin waves. So this Hamiltonian is not diagonal. So although usually in spin wave theory, we usually assume that spins are independent, they are actually not independent once you have 2 or more. And what is very interesting is that if you expand this, so again here, let's assume that we are talking always about long wavelength behavior. This is the way, again, this is the phase factor that I wrote here. So if you expand this to all wave vectors, to small wave vectors, what you will get is that the interaction scales as K dot P. So here you have a dimension. So let's call A as the lattice constant. So what is interesting is that unlike the Bose gas, when you have 2 spin waves, they don't interact with a hardcore collision, they interact through a very soft collision. And the way you can see this in simple terms is that imagine that I set this momentum P to 0, and I have a second spin wave. So if I apply a 0, so momentum 0, to the ferromagnetic ground state, what this is doing is essentially rotating the ground state. And as I argued at the beginning of my talk, there's SU2 symmetry, so essentially a global rotation of the ferromagnetic ground state essentially is not doing anything. You still have a ground state. So you will have a spin wave which would be freely propagating, and this term will vanish. So you will get exactly the single spin wave result without any interaction. If you have hardcore collisions, that wouldn't be possible. So again, in other words, if you have 2 spin waves coming and one has very low momenta, essentially what the spin wave is doing is kind of locally rotating the lattice globally. It's globally rotating the lattice, and the second spin wave will never see that there's another spin wave coming. So usually this interaction is kind of interesting because it will modify the behavior that we would expect from a conventional Bose gas. So far, so good? Oh.
Yeah, so within this gamma K, like this tau is over nearest neighbors?
Right,
or?
so this tau, so for example, if you have a square lattice, you need to sum, over the 4, tau 1, tau 2, tau 3, and tau 4.
Okay, so we'll just give like some cosines and so.
Yeah.
Okay, perfect, thanks.
But of course, okay.
I have a question. But in case you have scattering between 2 spin waves that are differentiated with like one very high moment and the other one very low moment, and do you have a sort of separation of, because here is both are small, I suppose, this expansion.
No, but even if one is large, so if I don't do the expansion and I said, actually, let's see if I set P to 0, you should get 0 here, right? So P0, you will get gamma Q minus gamma Q, P0, right? So
Sure.
if you just write the exact solution, just put P0 here and you will find, regardless of the way back, even if you don't do the expansion, you will get 0.
Thank you.
So now effectively, again, I emphasize that if you do the exercise at home of doing exactly the same, but starting from a Holstein-Primakov transformation, and you apply it to the Hamiltonian, you will get exactly the same results. You will get that the effective Hamiltonian describing a small density of spin flips in the system would be given by a quadratic term, where again, this one scales as k squared. And then I will have a nonlinearity or an interaction term, which would be k dot p. Again, here the interaction term will scale as also k squared.
So how does it look in real space, the interaction, then?
Sorry?
So if I were to write the interaction in real space, how would
You will have gradients of, so, well, I don't know if this is the right, so you will have something like a gradient of A plus Hermitian conjugate. So you will have something along these lines where you have gradients of the bosonic operators.
Okay. Well, it's very weird to imagine, but...
Is what?
No, it's weird to imagine.
Oh, well, no, think
so
about
this
it. Okay, let's assume I discretize this term. So
Okay.
this is operator on the next side minus operator on the I side, on the same. So essentially you get a sort of non-local interaction between nearest neighbors where you get a
Okay.
gradient. Yeah.
I see.
I don't know if this is the right form. I don't remember exactly how it looks, but you will get it in terms of gradients.
And how can I see it that when, say, like in this expression for like two spin waves, like if P was equal to 0, then like how does this correspond to a rotation? Because like, you know what, then I look at the formula for like SK dagger there and set up, say, K to be 0.
Mm-hmm.
Then like, you know what, this corresponds to like some kind of like a uniform.
Yeah, think about it that it would be the generator of the rotation in one direction, right? So so think about that you apply E to the I SK, and that generates global rotations of spins.
Okay, but like, why then K equals 0 is special?
K equals, in what sense is special?
So like, I mean, there's an expression there like K dot P,
Yep.
and you've argued that like if P is equal to 0, then we'll just
Oh,
like...
right, okay. So,
Yeah.
because essentially you will, so if you believe this thing that if I set P to 0, that this is just a global rotation, then you will have a single spin wave, right?
Yeah.
And you know that a single spin wave is an exact eigenstate of the
yeah.
Hamiltonian. So this term, this interaction term that I wrote here must vanish at P equals 0. Otherwise, otherwise it will be inconsistent that this is an eigenstate of the Hamiltonian.
Yeah, I guess my question is like, why is P equals 0 corresponding to a global rotation then?
So essentially what you're doing is you are, so P equals 0, you're essentially kind of flipping all spins, but with a, well, there's, I don't know exactly what angle it would be. There's a prefactor here that I don't know, but it would be the generator maybe we can discuss this later on, but this would generate the global rotation of all spins.
Okay.
Think about it as a generator of rotations
Okay,
of the
cool.
ferromagnetic state.
Thanks.
Okay, so how are we on time? Okay, good. Okay, so now we can at least, now that we have at least some regime, we can essentially repeat what I discussed yesterday for the, okay, let me make one comment also related to your question. In the case of a ferromagnetic state, you can think about spin waves are essentially the Goldstone modes of the order parameter. So usually Goldstone modes also have this, let's say, wave vector dependence in the interactions. It's kind of a more general result. The exact form, of course, is model dependent of what's the power here, but in general, you would expect that this should vanish. So now I can essentially repeat the same type of calculations that I did yesterday. Now that I have an effective bosonic theory, I can ask a situation, for example, where I start where an initial condition, something similar to what I'm showing in the slides, where spins are spiraling in real space. So it's kind of a product state. Where the angle of the spin has some initial wave vector, so essentially spins. So there's a net magnetization in one axis, and then the spins are rotating in the transverse direction of the angle of magnetization. So what you will find is that if I were to plot the spin-spin correlation function, for example, in the x, this would give you a delta function at wave vector q. So this is kind of the similar situation that I was discussing yesterday, where you can initialize the system into something that looks like a delta function at some given q, where with q you are essentially controlling the density, the energy density of the initial state. And because I'm assuming that there's a large magnetization, it's perfectly fine to use this effective Hamiltonian. And then the picture that will arise is exactly the same picture that I argue would occur yesterday, where if I start time evolving the Hamiltonian, what you would find is that there would be energy, and in this case, particle number, where particle, I mean the number of spin flips in the system, will try to reorganize itself. And you will have a cascade, two cascades, one of energy, a forward cascade of energy, where energy will try to flow towards the UV, whereas the number of, the distribution of spin flip will try to flow towards the infrared, and you will have some intermediate timescale prethermal regime with universal scaling exponents. In the case, the only distinction that with respect to yesterday was that now the interaction term would be different. That essentially means that when you characterize, so if I write the spin-spin correlation function, this would acquire, this is equal time. This is as a function of k. It will acquire some power law dependence, where the one I remember is in the case of energy. So you will have some, yesterday I didn't write exactly the power laws, but to give you a sense, usually you get, in this case, you get 10/3. So if you were to plot spin-spin correlation functions, you will see that you will get a universal power law with the exponent 10/3. And let me show you how it would look like if you were to do some numerics. If there's time, I can discuss later what are these numerics. So essentially, in a nutshell here, what I'm using is phase space methods, where, again, in this case, in fact, what is interesting is I'm starting with a state with zero magnetization. So even if you relax the assumption that you have a dilute number of quasi-particles, you will still see, so essentially I'm starting from an initial condition with some characteristic wave vector here where the arrow is placed. And what you will see is that you will get, in some prethermal regime, you will get this universal power loss. Here, I don't know what happened, but here, this is the flux of energy. So you will see that there's a constant flux of energy flowing towards the UV. If you were to, if you were to compute how energy is concentrated or how energy is distributed in momentum space, you will see that there's a net flux flowing towards the UV. So this is essentially very similar to what, again, to what I did yesterday. You can play exactly the same game. So for example, if I ask you,
yeah, so just to confirm, like, what are the timescales you're considering here? So this is a pre-thermal regime, or also like the infinite time regime, say? Like for this emergence of like those universal sort of like dependence.
So this is a prethermal regime. And okay, good. Actually, that's a very good. Let me make a comment regarding that question. So there's another interesting thing is that once you said, I'm not sure if this is related to your question. So once I said delta to 1, and you look at this Hamiltonian, there's no clear scale in the problem. And normally, like when you have a Bose gas, we're used to having like some sort of interaction parameter that I can tune. But if I give you this Hamiltonian, you look at it and you say, okay, what's the characteristic scale in this problem? And usually the characteristic scale would be given by the energy of the initial condition. So there would be an emergent weak coupling parameter, which would be the energy of the initial state. Relative to J. Let's put it, so let's write, so I can define a parameter. Now, let me not use this one. So you can write the energy of the initial state over the number of spins over J, which will tell you where you are standing if I define this X. So this X will define what's the typical scale of the problem. So again, I mentioned if this parameter is very large and you are in the middle of the spectrum, then you will thermalize in unit 1 time. But if I initialize the state in such a way that I'm not close to the ground state, but I'm at some finite, let's say 1/10 of J, that's the typical energy density per spin, then that would set your time scales of the problem. And then the closer you get to the ground state, the longer they would become.
And when you then thermalize, then like also those plots, like those phase diagrams you've drawn on the middle board, like those ones are also for a pre-thermal times?
These ones?
Yeah.
No, here I was asking in reality what happens at equilibrium, right? What happens at infinite times.
Okay, I see.
So here I was trying to do the same exercise that I was doing yesterday of asking the question, what are the relevant degrees of freedom if I just ask what happens at equilibrium, right? To get some insight from equilibrium physics of what could potentially be the processes that constrain thermalization.
Okay. So then those universal properties are for pre-thermal.
Correct.
Okay.
Right.
And then like at the very end, like how would the curve look like if we had just like, for a Boltzmann distributed, for a Gibbs ensemble or something?
Yeah, well, the Gibbs ensemble is the usual, what you would get. So a Gibbs ensemble usually, if I start from this Hamiltonian, the Gibbs ensemble this has an exponential dependence with energy, right? So it has exponential tails at the higher wave vectors. Here you have power loss, so it's more like a critical-like type of phenomena.
Cool, perfect. Thank you very much.
And again, exactly like yesterday, I can also play the same game. So let's assume I want to also study spatial temporal scaling exponents. So in this case, I'm looking at a snapshot at a given time where it's the figure that I just showed. Yeah, you are looking only at a snapshot, so you are fixing time and you are computing spin-spin correlation functions. You can also do the same exercise that I did yesterday of proposing, okay, let's assume that now I want to study spatial temporal scaling exponent as a function of wave vector. I don't know, I'm not gonna repeat the calculations, but you can do exactly the same procedure in which you write kinetic theory, which is essentially a theory. If I call this like a distribution function of spin waves, which would be true if you have a large magnetization. This can be this is essentially the density of magnons at some wave vector k, so the density of quasi-particles. You can write a essentially collision integral. You can plug in these ansatz for the collision integral. Then you have to use an additional ansatz, which in the context of spins, you have a constraint. Spins are constrained in phase space. So, sorry, the Hilbert space is constrained. So essentially what you would get is that if you sum, so this gives you one relation of alpha versus beta, so you need to close the relations using a second constraint or a second condition. And in this case, the fact that spin squared obey the relation n s plus 1. So here, if I sum all spin squared, I will get n times s plus 1. I can express this in Fourier space, s minus k. And here I'm summing over all components x, y, and z. And again, if I plug in this ansatz on this constraint, I will get a second relation between alpha versus beta, which you can essentially now solve algebraically, and you will find also the spatial temporal scaling exponent. So again, I didn't want to spend too much time in this because this would be verbatim from what I did yesterday. So there's nothing new. It's just applying the same type of analysis. So now comes the question of, so is there any questions so far about this? So let me ask a slightly different question. So far what I've been doing is assuming that there's a fix. So there's a state with a large magnetization, and I do a couple of spin flips. So in this case, I can make an analogy with the bosons, but now one may wonder if how really sensible is the fact to fix the order parameter, to fix the ferromagnetic state. In particular, I argued that particularly in the case of d equals 2, this may not be such a good approximation. And one may need to actually include additional degrees of freedom, this gauge degree of freedom of how you align locally your ferromagnetic ground state and include it and incorporate it into the dynamics. So I wanted to proceed with that. Let me do some simple scaling, mean field scaling. Again, let me rephrase the question. The question here is that I'm trying to ask is it feasible or is it reasonable to assume that if I start, for example, from an initial state that has no net magnetization, is this approximation of assuming that there's a local direction where magnetization will align, and I can start doing a spin wave approximation on top of that state, whether that's a reasonable assumption or not. And one can do a simple scaling argument. Like, for example, if I do a mean field argument, for example, let's take the Heisenberg model and I do a continuum approximation, assuming that I have some sort of texture of magnetization. So I orient the ferromagnetic state in different orientations. And let's assume that this has a size, this texture has some size xi. If you scale this, what you will find is that this will scale as xi d over 2 if dimension is different from 2, and this would be log xi d equals 2. Again, this essentially means, for example, if I'm in 3 dimensions and I want to create a spin texture in the classical sense, so I orient the ferromagnetic state in different directions, if I want to minimize energy of that texture, what I want is this psi to go to 0. So that's one reason why when you form, for example, topological defects in 3 dimensions, this would be very compact, very local objects, because you want to minimize the texture in your system. If you are in d equals 1 and you want to minimize energy, you will make fluctuations of S very large. So that's why there's no long-range order in 1 dimension. So there's no, usually these fluctuations will be, there won't be any long-range order to speak about in 1 dimensions. And the interesting case is 2 dimensions because it's a critical dimension. And essentially what would happen is that if you, let's assume I were to do a similar experiment where I start from, let's assume that now I have no net magnetization and I initialize a state with some fixed Q. So now I can no longer assume that so essentially this Q will define an initial scale of the problem. And below that scale, you will see fluctuations of magnetization that will that govern the, let's say, the infrared properties of the system. So now I can, again, the bottom line is that if you're in 2 dimensions, you will, these fluctuations of the order parameter will be relevant, and you have to incorporate it into your description. The question is, how do we do that? And again, here we can use semi-classical analysis. So this goes along the same lines of what we did yesterday. So if I write the equations of motion for spin degrees of freedom, so this is obtained by taking the commutator with the Hamiltonian. Again, here I'm expressing this in momentum space. And what I want to find is the scaling of the 2-point correlation function, SKA. Where from the equations of motion, it would be, this is the Levi-Civita symbol. So again, here what I'm writing is, so I want to find how this variable, the spin-spin correlation function, scales as a function using this, the same ansatz that I described below here. And what I essentially did is somehow similar to what I did with kinetic theory. You can write this spin-spin correlation function. You take time derivative. You use the equations of motions for spins, and you will get this on the right-hand side. So it's a term that contains 3 spin functions. Sorry, here is P. And now it's where we need to make some sort of scaling assumptions or some scaling guess of what we expect will happen. Again, remember that here the situation is that there's no net magnetization. So in essentially all components of spin are essentially equivalent. So I could take here AX, Y, or Z for A. And let me rephrase this in a slightly different way. And what I will assume is that there's only one scale in the problem. Somehow, this is very similar to what one does in coarsening dynamics. So what I will assume so rather than express it in time, I will express it in terms of scales. And the key assumption is that when so I will use a scaling argument, assuming that everything scales in the same form, all spin operator scales in the same way. What I will assume is that every time I see a spin operator, let me just use here I use psi for the typical length of the texture. So I will replace psi by alpha over 2 beta. Again, so this would be a relatively cheap way of doing the scaling, but I will argue later on that this is the right way because there's no other scale in the problem. And in particular, there's only, in particular, spin also is behaving classically because at longer lengths, they will try to order. So I can replace this 3-point correlation function. So this will scale as, let's see. So I have 3 spin operators, so I will have psi 3 alpha over 2 beta. Then I have an integral over momentum space. So this will give me an additional minus d. And here I missed the phase factor. So here there should be a phase factor of p, which will scale as k squared. And then the left-hand side, if I do the scaling, when you take time derivative of the 2-point correlation function, essentially you are lowering one of the times. So if this scales t to the alpha, this would be t to the alpha minus 1. So let me just equate both sides of the equation. So this would be e to the 3 alpha over 2 beta minus t minus 2. And on the left-hand side, I would have, let's see, e to the alpha minus 1 over beta. So essentially what I'm doing is assuming the scaling analysis, I'm equating both sides. I will get a relation between alpha and beta by assuming that they both scales the same with length. And at the end of the day, if you assume that this is 2-dimensional system, what you will find is that alpha equals 2/3 and beta equals 1/3. Again, let me just make a few comments. So the way of doing scaling, of course, it's a relatively cheap way of doing it, but there's a good intuition of why this actually works in the Heisenberg model, particularly when you're in the ferromagnetic state. In particular, I'm assuming that the initial conditions has no net magnetization. But also, if you think about it, in the Heisenberg model, the magnetization is not only the order parameter, but it's also the conserved charge. So it's the only degree of freedom that is only relevant. So that's why doing scaling in this way works fine. But for example, if I were to repeat this calculation for the antiferromagnetic state. So now, in addition to total spin, which is the conserved charge, you will also have a staggered magnetization, which is the order parameter. So now you will have additional degrees of freedom that you cannot just, let's put it this way, make them all scale in the same way. You have to do a much more careful analysis. And we did that in a different work, but in the case of ferromagnetic case, this actually works remarkably well because there's nothing else other than the total spin as a relevant degree of freedom. Let me show, no, this is not mine. Let me show how it looks in numerics. Actually, let me show you what actually happens. Let me explain. I forgot to put labels in this slide. So again, let's assume, let me explain what you are looking at in this slide. So let's assume I start at t equals 0. Here, what I'm plotting on the left is an initial state, which is a product state. So I'm plotting the local spin. So on the left, I'm plotting SIX as a function of position. So I'm plotting one local configuration of spin for each point in space. And I will define an initial state where there's a typical, an initial scale, which is xi. So it's the speed in which spins are rotating in space. So essentially here, this is a spin spiral. There's no z component. So the only thing spins are doing are rotating in xy direction in space. And if you go to Fourier space, and if you plot, so on the right-hand side, what I'm plotting is the spin-spin correlation function as a function of k. So basically, this quantity that I'm trying to scale. And this would be, so if you start evolving a configuration, what you will start seeing, and this is a semi-classical evolution. I will say a few words about the numerics themselves in a minute. But if you will start seeing is that you will see that, first of all, the order will be, the initial order that I started with will be very quickly washed away in unit 1 time, so very quickly. But as you start evolving at longer and longer times, you will see that there will be some characteristic scale, which would be start growing and growing. This would be very similar to what happens in coarsening dynamics. So these scales will start growing and coarsening, which is essentially this scale that I'm showing here. So this xi will start growing with time. And essentially, if you write from microscopic equations this scaling loss, you can, let me show you how it looks. So how it looks when you plot it as a function of time. So this is raw data. So for example, in the y-axis, I'm plotting as equal time spin-spin correlation function as a function of momentum. So as I mentioned in the initial condition, I have a peak, which is essentially this describing this spin spiraling in real space. As you let it evolve a little bit, you will see that the order will be destroyed, and then you will get some sort of distribution, which is evolving in time. You will see that there is a flow of spectral weight towards lower momenta. But if I rescale everything, so the spin-spin correlation functions and momenta with the parameters alpha and beta that I found analytically, you will see that there's a perfect scaling of correlations, of the spin-spin correlation function. And again, this is something that only survives in some prethermal regime. Any questions? So let me make another comment. You can also show, and this also goes back to the discussion yesterday, you can also show that regardless of what you start with, so if you start picking initial conditions which are different, for example, if instead of spins, for example, you can change the total magnetizations by changing the orientation of the initial spins. You can play around with any kind of initial conditions. And you will always find exactly the same scaling forms, the same scaling exponents, and similar. So here, essentially, what I'm tuning is the total angle of the initial state, and you will always find the same type of scaling. So this kind of elaborates on the idea that this is universal in the sense that it's not only just independent of the details of the Hamiltonian, but also it doesn't care about how you initialize your system in the first place. So this is as far beta for the local spin. Can anyone read the full question? For the local spin. I don't know which so maybe you can elaborate on the questions. What do you mean by local spin? Okay.
So I'm sorry. So I have a question. So how should I think about the timescales of like this pre-thermalization and thermalization? Like, is it related to the comment you've mentioned about the energy, like of the initial condition, and then, you know, if it's like large compared to like this n times j, then I'll, you know, well, if that thing is large, then basically I'll have like very short thermalization times, and this pre-thermal regime will be very short, or how should I think about the relevant timescales?
Right. So there's an initial timescale which is so let's put it this way. Let me show this in this plot. So this is the raw data, right? To give you an example. So there's an initial timescale where I wrote these dotted lines. So there you are eliminating all details of the initial condition. And usually that occurs on order J scales, so on microscopic scales. It's very fast. But then this intermediate scale regime is essentially governed by this, the only scale that I have left in the problem, which is essentially the energy density per spin over J. If this is very large, and I push it to the, let's assume I start from an infinite temperature state, so essentially that means that probably one way would be to point spins in random directions. So that would roughly look like an infinite temperature state. So in that case, you will not even see any prethermalization. You will just go directly to something very thermal very quickly on unit 1 times. So what controls this window is this parameter of initial energy over J per spin.
So for instance, if I had a ground state and I just like flipped like one or a few spins, then that would be like of order 1. So like that x would be 1 over n. So then like the thermalization time should be of order n. Like
well,
still.
if you have one spin, you know, that's an eigenstate. So then, well,
No, I mean like I just flip one of the, well, okay, I introduce one spin wave, right?
Right, that would be kind of like a non-interacting type of spin wave because.
Okay, so suppose like 2 or something, right?
Sure.
So then like I just raise up the energy by order 1, say, like with respect to the ground state. So then I should expect, you know, like the full thermalization to happen on the timescale of like order n. Like, is that thing roughly
right?
correct?
It will take a while to thermalize. Also, well, if you have only 2 spin flips, you will be in the regime that I was describing here, where you are in you really don't have magnetization fluctuation. So essentially, most of your spin are pointing up. So this thing that I described here, where you wonder whether the orientation of the total magnetization is important, if in the case you are describing, this probably would be completely irrelevant, and you can just find all the relevant scaling exponents from just plain kinetic theory. So from this analysis. But if you flip half the spins, but you still have some sort of finite energy, then this is when this type of analysis applies. You will have fluctuations of the order parameter or that would be relevant in a long-lived prethermal regime.
Okay, so in general, I should just think of the timescale to thermalization going like roughly like 1/x, like you've written there.
Yeah,
right?
probably.
Okay.
That should be very I don't know if that's the exact result, but it should scale with 1/x.
Okay.
Yeah.
Okay. Cool. Thanks.
Okay. Yeah. In the local spin concept, in the electron flux, in the time scale. Yeah. Maybe, yeah, I don't understand the context of the question of where, but can I actually talk to him after I can reply to him by chat, because it may be easier or to maybe directly chat than trying to guess from just reading the message. Are we past time? Right, but I don't want also to push everything. I mean, I can finish here and continue tomorrow. Let's do that, so otherwise there's no cascade towards the afternoon session.
Do you have any more questions?
So all the analysis in some sense based on spin wave theory, right? In some sense, isn't this result some kind of classical hydrodynamics kind of thing?
Yeah. Well, as I mentioned yesterday, always I will be looking some classical description of this prethermal regime. So in this case, that's why I mentioned at the very beginning, you can consider a spin 1/2, which you would naively associate to a highly quantum, but because effectively what you have is some collective behavior at sufficiently long waves, length scales, you are averaging out the behavior of many spins, and you will get effectively a classical description.
I see. So if I would add more terms to the spin wave Hamiltonian, which would contribute suppressed as 1/s, say, the results would be the same for the exponents in some sense.
Right. If I start pushing S to infinity, if you want, you will get exactly the same results. That's why I didn't put too much emphasis on spin number. In the antiferromagnetic case, it may be different because in that case, the ground state is, so okay, let's assume I repeat everything now. I repeat the entire lecture and I just flip a sign here. And I start asking what happens with the ferromagnetic state. You may wonder whether this small s will suppress the tendency towards ordering, and then you will just you wouldn't have this problem that I described here. But actually, there are a lot of papers a while ago, maybe in the early 2000s, where the belief is that even for square lattice, for spin 1/2, you still have antiferromagnetic order. So actually, everything else will still translate, and you can build the same semi-classical description of dynamics.
Okay, I see. Thanks.
And those results would hold also for like delta not being equal to 1, or which of those things would translate?
Good. So let's assume I pick a different delta. Actually, I skipped that slide. Which is this one. So if I essentially have a delta here, which is not equal to 1, I'm breaking SU2 symmetry. So now you have a preferred axis where you analyze everything. And if I were to repeat all the same calculations, what you would find is that the collision term is no longer soft. There's a hardcore component. So that will essentially change all the scaling exponents. You can still apply the same type of analysis, but what would change is that now you will see a different universal regime simply because you have a different symmetry. And that's, for example, in this figure. In this figure, essentially what I'm doing is precisely that. I add a large delta, which essentially suppressing fluctuations in the z direction. And if you do the same type of experiments, numerical experiments, you will see that, in fact, there's not just one, there's two potential power loss that could arise in numerics. So you're essentially changing the numerical value of the scaling exponents. But the analysis you can probably do roughly the same.
So then in what sense is this universal, like independent of the parameters of the Hamiltonian? Like what are the parameters I'm
No, but think that when you change delta, you're changing the symmetry of the Hamiltonian.
Okay.
So symmetries are always, essential in the discussion. So if you change the symmetry, it's not surprising that you're also changing the exponents.
Okay, okay, I see. Okay, cool, thanks.
Okay, more questions?
Just a clarifying question. In this case where we're dealing with like our initial state is texture, magnetic texture, are we still using Holstein-Primakov or?
No, I never use Holstein-Primakov in this case. I just did scaling of the microscopic equations of motion. So there's no spin waves in this case.
Okay, so we can thank Nieva for the lecture.
Yeah.
And we have a lunch break and see you all at 2:30.